Okay, so now let's talk about the proof of correctness. So we know that what we're doing is starting at S, starting with the distance from S to S is 0, the distance from S, the estimated distance from S to everything else is infinite. And then for each edge incident to S, we update the estimate and we say, okay, well, now we can see we can get from S to U in with distance 10, and we can get from S to X with distance 5, and so we update, we refine. It's called in the book. It's called relaxing. We relax these estimates. We shrink them, and then, but we haven't definitively set the distances to U and X yet. So what happened? We've set the distance to S. So when we're doing this, we've set the distance to S as 0. And then we have this estimate of the distance to U, and we have the estimate of the distance to X. So we take the smallest of the estimates, and we add it to this tree. And then we update the estimates of all of the things which we can reach from X. And we take the smallest and we fix that distance and we add it to the tree. So in this case, it's and then we update the estimates of the distances, things incident to Y, and we take the smallest thing we can reach in one step from the tree, which is U. And we update the estimates, and now we take the smallest thing that we can reach in one step from the tree, which is B. Okay, and we do that that updating using the priority queue. So why is this correct? Well, suppose that at some point okay, again, let's do this the proper way. Before we take any steps, this is a greedy algorithm. At each step, we're taking the thing whose, we're taking the vertex that we can reach in one step from our current tree, whose distance is smallest. Okay, so before we take any steps, so this is greedy, before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after we take I steps, our subsolution can be extended to an optimal solution. So this is going to be some tree T sub I. Okay, and then at this point we have these vertices that we can reach in one step from vertices in T. Okay. So we can reach the red vertices in one step and we look at all the things that we can reach in one step from T, and we take the smallest one. And we say, okay, we're going to add that to the tree. So suppose it's the distance to this vertex plus the distance from this vertex to this vertex is minimum of all these estimates. So we're going to take this into the tree. Okay, and this becomes green. Okay. So why is, and then we're going to take everything that we can reach from there and see if we can reach anything new or update the estimates. Maybe we can reach this one more cheaply or this one more cheaply going from here instead of from here or from here. Okay? So why is this correct? Well, suppose it's not correct. So remember we had ti. Well, let's just erase. Let's just change ti back. So we want to take this one. So we want to take this one across this edge. But suppose that when we set this distance, it's incorrect. Okay? That actually what we should have done was, instead of going from S, which is somewhere here, to here, and then to here, it's better for us to go from S to, say, this one, to this one, and then take some path around. Okay? This would be better than going from here to here. Why can't that happen? Well, I said that Dijkstra's algorithm assumes that there are no negative weight edges. So if the distance from, so this is distance from S, this is distance D, and yeah, this is distance, this is a distance, okay, let's say that this is S, this is, okay, I'm going to use, what's some other variable name, some other vertex name. This is A, and this is B. So A, we've already calculated distance S to A, okay? This is stored here. So now, and let's say that this is C and D. So at C, we have stored distance SC, written in blue. And so now we're saying that, okay, it's better to go from, we think it, Dijkstra's algorithm goes from S to A and A to B, to go from S to B. But we're saying, suppose it were shorter to go from S to C, C to D, and D to B. So that would mean that distance SA plus distance AB is greater than distance SC plus distance CD plus distance DB. But that can't happen. So why? Because we assume that written at B is distance, the shortest way to get to B is from in one step from any of these is written here. And if we're assuming that it's distance SA plus distance AB, and written at B will be the shortest way to get to D in one step from anybody in here, then it will be distance AC plus distance CD. But we took the number that had the smallest estimate. So we took B because the number written here was smaller than the number written here. But that means the distance SA from S to A plus distance A to B was bigger than distance S to C plus distance C to D. So that means that just getting from S to D is at least as expensive as getting from S to B. So unless the only way that it can actually be cheaper to go from S to C and then to D and then to B is if this path has negative cost. So yes, in the case of negative edge weights, Dijkstra's algorithm breaks. But if there are no negative edge weights, then it's correct. So if after I steps we've chosen our tree correctly, and we have the right numbers written in all the red vertices, then when we choose the red vertex, the vertex with the smallest number written in it, the fastest way we can get to that vertex is in one step from our tree. Okay, so that's why it's correct. And then you say, okay, so suppose that after I steps, our subsolution can be extended to an optimal solution. Then after I plus 1 steps, our subsolution can be extended to an optimal solution. Therefore, by induction, we get an optimal solution. Okay, so I'm going to pause this again.